Welcome to this video. Hope you're doing good. Today we'll try to solve an array problem which has been classified as easy. Okay, so let's read the problem statement. So the problem says that given an array of integer nums which is sorted in ascending order. Okay, so keep in mind that the array has already been sorted in ascending order, and we have already also given an integer target. So we have to write a function to search target in nums. Okay, we have to determine if target is present in nums or not, and if target exists then we return its index, else we return -1. Okay, so the problem, I hope the problem is clear. Basically we have been given an array nums and a value target, and we have to check if target exists in this array or not. If it exists, we return the corresponding index at which it is present, else we return -1. Okay, great. So let's assume this is the input array and the value that we are trying to search, say for, is 12. Okay, so we already know that 12 lies in this array, but how do we search it? Okay, so one approach obviously could be that we iterate over this entire array. Okay, and for every index we check if the value at that index is equal to our target value or not, and if it is equal then that corresponding index is our answer and we return it. If, say for, we reach the end of the array and we don't have any more indexes to iterate over, then we know that the target value is not present in our array, and then we return -1. Okay, so very straight. So I'll use Python to write this small code, but a very small code for this could be for I in range n if nums I is equal to target, then we return that corresponding index. Okay, and say for we come out of the loop and we still haven't returned, that means no value in the current in this array is equal to target, so we return -1. Okay, so like this will be our simple code. Okay, and it should work fine. Okay, talking about the time complexity of this solution, so if you observe that in worst case we will have to traverse the entire array, that because our target, it might be present at the last location or it might not be present in this array at all. So in worst case we will end up traversing the entire case. So the time complexity of this solution would be big O of n. We already have a solution which is good, but let's see if we can try to find a more optimized solution. Now in the question we have been given that the given array is in sorted form. Okay, so let's try to come up with another approach which is based on binary search. So I have copied this array into a new tab. So talking about binary search is a search algorithm which is used to find the index of an element in a sorted array. Let's see the algorithm. So to start with binary search, we first have to define a search space in which we'll be searching for the target element. So I'll quickly adjust this. Okay, now in this array our target element can be present at any index. So what we will do is we will start by defining a search space over the entire array. So we will use two pointers, low and high. Okay, which will be located at the two ends of this array. Now to start with binary search, we first go to the middle position of our search space. So how do we find the middle position? We find the middle position using mid is equal to L plus H by 2 and we take an integer division. Now in this case it will be 0 plus 6 by 2, which will be equal to 3. So this lands us at index 3. Now if you remember, like from the previous example, the target value that we are trying to search in this case is 12. Now value 1 is less than 12. Now what does this indicate? This indicates to us that the value present at index 3 and value present at all the indexes which is less than 3 is less than 12, because the array is in sorted order. So if this value is 1, then all the values before this index are guaranteed to be less than or equal to 1. Okay, now this tells us that since our value is greater than the value present at index 3, so this tells us that our target value cannot be present from index 0 to index 3 because all of them are smaller. Okay, now we modify our search space by shifting our low index to the right of mid. So now low will now point to mid plus 1, which is equal to 4. Okay, so now low is equal to 4 and high is equal to 6. Okay, using the same method that we used in the previous iteration, we find the midpoint of our search space, which is equal to 4 plus 6 by 2, which is equal to 5. We land at index 5, whose value is 5. Now again this value is less than 12, so we can again discard this search space as well and move to this search space. So writing here now low again is equal to mid plus 1, which is equal to 6, and high is also equal to 6. Now in this case the midpoint of our search space will be 6 plus 6 by 2, which is equal to 6 again. Okay, now we see that at index 6 our value is equal to our target value. Okay, so we return this index 6. Okay, so this is how binary search works. And for example, had it been a different value, say for 10, okay, so in this case our left would have again moved by 1 pointer to the right. Okay, and in this case the search space would have become invalid, because now the left pointer, it now basically is greater than the high pointer. That means our search space is now exhausted and we are not able to find the target. So in this case we would have simply returned -1. Okay, talking about the time complexity of binary search, if you observe closely, in every iteration we are basically reducing our search space by half. So if you remember, like in first iteration we discarded this half of the array, and in second iteration we discarded this half of the array, because in every iteration what we observe is that we either move to the left of our mid or to the right of our mid. That means that one half of the array is discarded. Okay, so the number of steps it takes to cover the entire search space, or in this case the entire array, is basically log of n to the base 2, where n is the size of our array and 2 a factor of 2, because at every step we are discarding half of the array. So the runtime complexity of a binary search solution in this case would be log of n to the base 2, which is much greater than n that we derived in the previous solution. Okay, so let's try to code up this solution and see how it works. Okay, so I'll come here. Okay, so as we saw in that example, so we define our search space as low and high. Low will point to the start of the array and high will point to the end of the array, which is length of nums minus 1. Now what we will do is we will keep looking for the target till our search space is valid, while low is less than equal to high. We find the midpoint of our search space, which is equal to low plus high by 2, and we see if nums mid is equal to target, then we return mid, because we are able to locate the target in our array. Now but say for if the value at the mid index is less than target, then we discard the left half of our array and move to the right half of our array. So left will be equal to mid plus 1, else right will be equal to mid minus 1. Okay, and say for during the entire search, if you are not able to reach this statement, basically we basically exhausted our search space and we are still not able to find the target, then we simply return minus 1, indicating that we are not able to find the target. So let's try to run this code. Okay, it's taking some time. Actually a lot of time, and it says okay, I'm sorry, I used the wrong variable names. Okay, let's try to run this, and it is accepted. And okay, so I think this gives us a pretty good percentage as well. Okay, so I hope this makes the concept of binary search a bit clearer, and in the next set of videos we'll be looking at more applications of binary search and other questions as well. Thank you for watching.